This is pretty much the exact setup from that standard answer. I've got a vibration generator over here, my jigsaw from the garage. The string is running across there, and I'm using this little phone mount as a pulley, and I'm hanging a big heavy carabiner on the other end as my weight. Yeah, so it's basically the exact same setup from the question in the book, and I'll show you how we can make the different harmonics on this wave. Maybe this will help you understand a little bit more what harmonics are all about. Today we're going to have a little look at harmonics. It's got lots of diagrams, but it's not actually that complicated. The only piece of advice that I'll give you guys is bother yourself to draw it. The rules are simple, you just need to draw them, sketch them out and work out what's going on. You might notice that in order for a standing wave to form, on a string or using EM radiation, it has to have a node at both ends. You can't have a stationary wave where there's a maximum at this end, because it doesn't work. You can only get reflection from a node. For that reason, this arrangement shown in the book, the fundamental, is really important to recognise. This is the fundamental frequency, or the first harmonic, because it's the first one that can possibly form. We cannot get a stationary wave at a wavelength longer than this. That is the fundamental first harmonic. We can get others wherever there is a node at the reflected end. So, for example, the second harmonic, we could have an entire wavelength, and we could have a node here and a node there. That's allowed, but we couldn't have any other fraction because we wouldn't get a node at both ends. It's that simple, guys. Are you going to be able to get a node at the end? If yes, great, you've got a harmonic. If not, it won't work. In this case, you can see that the length of our string is a full wavelength. Have a look at the examples regarding this. You'll notice for the first harmonic, there's one antinode. Second harmonic, 2 antinodes. Third harmonic, 3 antinodes. And remember, for the most part, it's not the length of the string that's changing, that's fixed. It's the number of little bits of wave that you can see on that string that is changing. That means that the wavelength is changing, the frequency is changing. Like all waves, it's the speed that remains constant on that piece of string or in that situation. I'm lucky enough to have a well-stocked garage. You'll notice if I pluck the string, I can generate the fundamental frequency anyway. So if I give it a twang, that is the fundamental frequency of this string. I can't get it to give me it using the jigsaw, I think it's just too fast an oscillator. But here you see the fundamental, node, and I'm making the antinode in the middle. This jigsaw can generate the second, third and fourth, etc. harmonic because it vibrates really quickly, and I'll show you that in a second. I'm not wearing my tie or my regular clothes because I feel like it might get caught up in the jigsaw. And I've used a black background so that you can just see this string when it's vibrating. Let's see what happens when I turn the jigsaw on. Through the magic of video, so what you're seeing here is the second harmonic. It's got 2 antinodes. The length of the string is equal to exactly the wavelength of one of those waves. If I increase the frequency, you see the third harmonic. In this case, there are 1.5 full wavelengths along that string. It has 3 antinodes and 1, 2, 3, 4 nodes. Increasing the frequency further, I can just about get the 4th harmonic on this string. That has 4 antinodes. You can see there's 2 complete wavelengths along the length of this. Now to adjust the speed setting to go any further. Anyway, that was really fun, you get the picture. Again, these waves only form where there is a node at the end where they're being generated and a node at the end where they're being reflected. Stationary waves only form under certain conditions. For a stationary wave on a string, the length is an exact multiple of half of the wavelength, either half, 1, 3/2, 2, you can't have that, then a stationary wave will not form on that string. This relationship between length and wavelength is used in general calculations, usually just V equals F lambda calculations. Have a try at these questions and see how you feel about them. Check your answers periodically too. Hopefully the harmonics on a string aren't too hard to understand. You've got a fixed length of string, you must have a node at both ends. It's possible to have a harmonic in a pipe, and this is, you know, the idea behind organs and musical instruments like that, pipe instruments, wind instruments. You get a stationary wave in it, but one of the ends is open. This explains why you can, you know, blow a empty bottle and get a note out of it. Short, long. It's because you're forming this stationary wave here. Wherever we have an open end to a pipe, we have an antinode, and wherever we have a closed end, we have a node. It can change the condition for our fundamental frequency, and basically, guys, just sketch it out. Know that open ends form an antinode, closed ends form a node. So we can see our fundamental frequency for an open pipe can be a quarter of a wavelength. The next harmonic is 3/4 of a wavelength, and then it's 5/4 of a wavelength. Sometimes you'll see this listed as the first, third, and fifth harmonic, but usually they just ask, you know, what is the next harmonic that can be formed? Sketch it, draw it, tell me what we see. Always sketch it out. If you're not sketching it out and you're getting it wrong, the first thing I'm going to say is sketch it out. We might have a pipe with 2 open ends. That's perfectly possible as well, and in that case, it's an antinode at both ends. That means there must be at least one node in the middle. It looks different, but the conditions in this, it's the same as having a closed end at both ends. We have half wavelength over here. This is a whole wavelength. You might have to verify that for yourself, but it goes from a maximum to a minimum to a maximum. That is a whole wavelength for the second harmonic, and then the third harmonic. So actually the only condition that is different is where you have a open end and a closed end. If you've got a pipe where both of the ends are open, it's the same as, say, a string where both of the ends are closed. I like this little demo just to demonstrate what's going on. The way that we sketch it like this is not quite true to what's happening in the pipe like this, but you can't sketch that, and you're not supposed to. That's just to show you what's actually going on. Particles are moving forwards and backwards, they're not moving up and down. But we always sketch it like this because it's a visual representation of what's going on, and it's the easiest to understand. Just to close up and summarise, there's this table. If it's not in the booklet, I think it's definitely on the summary sheets, so get those summary sheets out and complete them. Comparing stationary waves, what we've been talking about this week, with progressive waves, the type of waves that you have always known. Stationary waves store energy, whereas progressive waves transfer energy from one place to another. The amplitude of a stationary wave, it varies for each particle on that wave. So a particle on a node will have an amplitude of 0, but a particle on an antinode will have a maximum amplitude. Whereas on a progressive wave, as that wave moves across, each particle would eventually reach the amplitude and it'll go back, and so every particle gets that chance. The phase on a stationary wave, well, we talked about it earlier. Every particle on an antinode is moving in the same direction at the same time. So they're all in phase. Phase asks what direction they're going to be moving in. Across a node, well, one antinode will be going up, the other one will be going down, and vice versa. So there's a change, a phase difference of pi, 180 degrees, between one antinode and the next one I'm on. I like to say that's a phase difference of pi across nodes. The phase on a progressive wave, obviously, that's going to vary depending on where you are. Each individual particle on a progressive wave will have a different phase because it'll be moving at a very slightly different rate, in a very slightly different direction to all of the other particles on that wave. This is a really good little summary comparing the two types of stationary and progressive wave. Just learn the things in this box and make sure that you're aware of them. I know I've gone through this really quickly, but take your time, go through it, try and understand it. If you can do these and you can answer the end of topic questions, then congratulations, you've understood stationary waves, and with it, one of the most complex ideas in the whole of electrons, waves and photons. If you like it, if this is your thing, fantastic, because you're going to pick up marks where nationally lots of people won't. And the next lesson we're going to move on to photons, but it's a very short book. So I recommend that you take some time next week to do one revision page on the basic ideas in waves and one revision page on these more complicated ideas involving superposition. That will really help you just to consolidate everything, keep it together so that you can refer back to it when you're revising very quickly, but also because it'll probably help you understand things better. Have a try.